All right, this is day 12. This is our third and final day on the section of where does our data come from? And today we're talking about experiments. So, for the longest time, we've been saying correlation doesn't imply causation. Just because we have two variables that co-vary, that have a very strong association, doesn't necessarily mean that one of them is the cause of the other one. Today, we are finally going to be able to make a statement like that. We are finally going to be able to pin down that one of these variables is in fact causing the other one. Today, we're finally going to be able to make some sort of causality statement. And at the end of it, there will still be some wiggle words, we think that this is likely the cause of something else. But at least we're talking about causation now. Okay, so the running example that we're going to use for this video is talking about the association between aspirin and blood pressure. So we imagine, or we suspect, that taking aspirin has an effect on someone's blood pressure. That the act of consuming this aspirin, or the presence of the aspirin in the system, is what's causing, let's say, a lower blood pressure. Last time we were talking about observational studies, and an example of an observational study about these would be maybe you record your blood pressure every day, and you also record if you've had an aspirin every day. And you can see if these variables are varying in the same way. And the problem with that approach is that maybe there is some sort of lurking variable that's affecting what's going on. Maybe there's something that we're not accounting for. Perhaps on days in which you're stressed, you're both more likely to take aspirin and have higher blood pressure, or, vice versa. So the issue is that we want to be able to nail down and get rid of these extra variables. We get around a lot of that with experiments by having our experimenters take an active role in determining which treatments various subjects get. And we'll talk about this terminology moving forward, but in a similar way to how we determine our samples in the first place, we're going to use randomization to put the subjects, the individuals, into various groups that we can then compare. So the fundamental idea behind experiments is that we're going to be comparing different, let's say, in our aspirin and blood pressure example, we're going to be comparing different dosages of aspirin to each other. And the idea is that we're setting it up so that the difference between groups should only be the thing that we're studying. Okay, so that's the overview. Let's unpack that a bit. The first step is to identify what exactly it is that we're studying. So what I mean by that is we want to identify the explanatory variable or variables and the response variable. The idea is that something is causing something else. So the explanatory variable, which is often called a factor, in this case would be aspirin. Whereas the response variable, which we often just call the response, is going to be the blood pressure. So our hunch, the relationship that we're actually interested in is that we suspect aspirin is causing a change in blood pressure. And then once we have these variables identified, we're going to use randomization. So we are going to randomly assign the subjects. So in this case, the subjects would be the collection of individuals chosen for the study. And we talked on Monday about how we want this collection of people, or a collection of objects, or whatever it is we're studying. We want this collection to be a representative sample of the population, which typically means using some sort of randomization technique to select these people, or these whatever experimental units we're studying, to select them from the population as a whole. Okay. So once we have that collection of subjects, we're going to again use randomization to assign, to break this set up into multiple groups, to assign each subject to what we're calling a specific treatment. So in our aspirin and blood pressure example, maybe we are dividing our subjects up into 3 different groups. One group takes no aspirin, one group takes 1 aspirin, and one group takes 3 aspirin, or what have you. The structure is that, or the point of this is that out of our representative sample, our collection of all of our subjects, we are going to divide them up into groups that we think are also representative. And by doing so, in theory, the only difference between the groups moving forward should be their different treatment levels. All right, so what goes into the process for designing an experiment? And there are 4 sort of main principles that the book likes to talk about. The first of which is that we want to control these extra sources of variation between the groups. So if we are studying the effect of aspirin on, different people, and we've divided our subjects up into different groups, there's natural variation between these groups. That, there's obviously different people in each group, so there's going to be some differences. The idea was that by randomly putting them in each group, and by trying to keep what's happening as similar as possible between the groups, we are eliminating, ideally, some sort of other factor coming in and influencing what's happening. So for our aspirin and blood pressure example, perhaps we are instructing everybody to take or not take their aspirin at the same time of day, to measure their blood pressure at the same time of day, to try to keep these groups as similar as possible, to avoid there being some sort of extra factor coming in. Okay. All right, so one caution here is that there is such a thing as over-controlling. And the problem with restricting the scope of the study too much is that we can't generalize the results very well. It could be the case that, so let's say in our aspirin and blood pressure example, we are having everybody take their blood pressure and take or not take aspirin in the morning. Maybe the results are going to be very definitive for morning aspirin and blood pressure use. What about in the afternoon? So by controlling our experiment too much, we run the risk of it not really saying all that much. So there's a balance between what exactly you want to control and what you want to, leave up to chance. I've already mentioned this second principle, and that is that we want to randomize the assignment of the participants, of the individuals, into the different treatment groups. And the idea behind this is that there's always going to be some variation between the individuals in these groups. And we're not going to be saying that, hey, each of these groups are identical. The point of the randomization is to equalize the effects of these unknown or uncontrolled variables. A phrase that gets thrown around sometimes is that you want to control what you can and randomize the rest. Since we're throwing around this whole randomization a lot of these experiments are really a numbers game. What I mean by that is we need to be able to replicate them in order for them to actually have some sort of meaning. If, you know a friend who took aspirin one day and had low blood pressure that day, that is certainly by itself not enough evidence to say that, hey, there's something going on. So when we say that we want to replicate this effect, we mean that in a couple different ways. We want that an individual study to have more than one subject. In other words, we want a reasonably large sample size. We want to be able to replicate the effect of this increase or decrease in blood pressure across multiple subjects. But we also mean that we want to be able to replicate the experiment as a whole in other situations, in different parts of the world, different, maybe our first study was mostly focusing on college age people. Maybe we also want to focus on older people. We want to be able to replicate the results across different demographics. All right, this last principle is certainly more optional, but it's an important idea that we need to bring up as well, and that's that we have the option of blocking our subjects, but in other words, by pre-dividing them into different groups. I particularly like the books example in this one. Let's say that we are studying something to do with balance as our response variable, and the collection of subjects has two people who are gymnasts. Well, if we entirely randomly assigned the subjects into different groups, then it's certainly possible that those two would end up in the same group. And that might have some somewhat dramatic effect on measuring balance. Let's presume that they are especially adept at balancing. So one thing we can do, one way to address that, is by blocking. And what we mean by that is we're going to first divide our sample, our collection of subjects, up into different groups based off of some demographic, in this case, gymnast or not. And then we're going to divide them up into the whatever different treatment levels we might be assigning. So for blocking, I find it's usually really helpful to draw a picture, just to have some sort of diagram for what we mean. All right, here's an example of what I mean by a diagram. So let's start off with an example that doesn't use blocking, but in this first picture, what we're doing is we're taking our sample and we are dividing participants, we're dividing the subjects up into two different groups just by using some sort of randomization technique. So people are randomly assigned to group 1 or group 2, and the people who are in group 1 get treatment 1, maybe they don't take an aspirin. People in group 2 get treatment 2, maybe they're instructed to take an aspirin. And then at the end of the study, we're going to compare the two different groups. In contrast, here's an example for a diagram for this gymnast versus not balancing example. Since we suspect that the gymnasts in our sample might have different reactions to whatever balance measurement study we're doing than non-gymnasts, then one thing that we can do is first divide them up into separate groups, and then out of the group of gymnasts, we're going to do sort of the exact same thing that we did in our non-blocking example. We're going to randomly divide the gymnasts up into two different groups, and those are going to get treatment 1 or treatment 2. At the same time, we're going to take all of the non-gymnasts, we're going to take everybody else, and we're going to divide them up into two different groups. And they're probably going to be getting the same pair of treatments. The point is just that we want to make sure that this extra distinction that we've decided that is significant is accounted for and treated separately. So we can do this with any demographic that we think is important enough to warrant subcategorizing our subjects. The reason that we wouldn't do this with a ton of individuals is that, well, in a little bit we'll be talking about sample size considerations, and we want a reasonably large sample size in our study, but we also want to make sure that within the study, each group that we're working with has a reasonably large sample size. And if we go and use too many blocking techniques, then we are likely going to end up with some of these groups being just too small. So common attributes that are typically blocked for are things like gender or age, but really any demographic can be something that an experimenter might decide is significant to the study and can be broken up into these different groups. All right, there's a few more ideas that I want to touch on. The first of which is this notion of a control group. So it's usually a good idea to have one of our treatments, one of the levels in our study, so have one of our groups be assigned the boring case, the nothing's changed, or the run-of-the-mill, situation. And by doing this, that allows us to make this direct comparison of the thing that we're trying to study versus the status quo. So by having one of the groups be the boring, the do-nothing group, that allows us to make the comparison to see if the thing that we're actually studying is an improvement over a baseline. Having a control group establishes that baseline. Another important idea to touch on is this notion of blinding. So just by being aware that you're in a study, or by being cognizant of the fact that or by paying attention to what you do on a day-to-day basis, or what have you, you can either consciously or subconsciously impact the results of the study. Let's say if the balance study I was talking about earlier was measuring how well you can walk across a balance beam, either wearing or not wearing a hat. Well, maybe you think that, the hat is definitely going to help, and by having that assumption, that expectation, you go into that attempt with more confidence, and then therefore do better. And the point I'm trying to make is that the participants being aware of what's happening can impact the results in surprising ways. And this is true even in in medical senses. There have actually been a lot of studies that just by thinking that you are getting a medication that can actually have an impact on a disease recovery or whatnot. The mind has a surprising amount of control over some aspects of, overall health. So this is where the idea of a placebo would come in, is that if we don't want these subjects to be aware of which treatment they're in, as in, do they, what level of some drug they're getting, to hide that information from them, we use what's called a placebo, which is, in a sense, or often referred to as some sort of fake sugar pill. So something that has no effect, but feels the same, looks the same, tastes the same as an actual drug or what have you. And so that this would apply for any study if there is some way of tricking the participants, the people in the study, to not knowing which group they're in, that can help prevent some sort of bias that's introduced by the individual expecting something or another based off of what treatment level they're in. All right, so it can be important to make sure that the individuals, the subjects of the study, don't know which group they're in because they may consciously or subconsciously affect the outcome. It can also be important that, if possible, to prevent the people running the study from knowing which group the participants are in. If, let's say, a doctor or a nurse happens to know which individuals are getting an actual treatment drug versus a placebo, then maybe their mannerisms or their attitude towards these individuals might convey something subconsciously or have some other impact on the results of the study. So when we typically say that a study is blind, what we mean is that the subjects, the participants, don't know which treatment they're in. When we say that it's double blind, what we usually mean is that neither the subjects nor the people running the experiment know who has been assigned to which group. Obviously, that's being recorded somewhere. Somebody knows who's in what group, but maybe that's written down, or someone who's not actually interacting with these people can keep all of that straight. Okay, so a lot of considerations go into what makes an experiment? How do we design some way of testing some sort of causality relationship between two variables? And at its core, the idea behind all of this is that we're trying to eliminate any possible variation between groups other than the thing that we're trying to study. If we can eliminate everything else, and the only difference between two groups is which treatment they got, as in did they take aspirin or not, and we see that they have, on the whole, notably different blood pressures, then we can actually make some sort of causality statement. And we still have to be careful with how definitive we are. A lot of this stuff is probabilistic, but we can say something along the lines of, our experiment suggests that taking aspirin once a day reduces your blood pressure, a certain amount. And the reason that we're able to say that is because we've accounted for everything else.